So today I'd like to talk to you about how to infer interaction between species using time series. And for this, we'll use two kinds of methods, Granger causality techniques and convergent cross-mapping. So this is some work I've done at the Institute of Mathematics of Bordeaux, where I work in the CNRS, French Research Institute, together with Coralie Picoche, who's PhD student there as well, and in collaboration with Matteo Detto, who's at Princeton, and Florian Artigue, who's at the University of Regensburg in Germany. So when we think about interactions in ecology, we can mean very different things. So it's important to stay precise on exactly what we mean. So here and in the remainder of the talk, I will think about an interaction network in a dynamic sense, not only who eats whom, well, not who eats whom, but who has an effect on whom. So we would consider that there is an interaction if the population growth rate of species I changes as a function of changes in the density of species J. That would be an interaction from J to I. And that corresponds in the diagram to the black arrows. So we would say, for instance, there's an interaction from lynx to coyote if the population growth rate of the coyote is affected by changes in the population density of the lynx. And that's a different thing from who eats whom. You can have a larger trophic network, for instance, but this may not necessarily affect population fluctuations. So these dynamic interactions in a dynamical system sense, we can try to infer them from time series data. You have on the right an example where you have a prey, which is fluctuating in blue, and you have a predator, which is fluctuating in red. And it just so happens that, as you can see, the predator time series is slightly shifted to the right, which means there is information in the time series of the predator that it follows its prey dynamics. So there's probably a link from the prey to the predator. So actually, in that case, as we will see, there's also a link from the predator to the prey. But this is to say that in this, in making inference of interactions using time series, we're using the notion that the cause precedes the effect. And an important statistical tool that makes more precise this notion of the cause precedes the effect is Granger causality. So just to give a definition, we say that X Granger causes Y if when I include time series X in a time series model for Y, it improves the prediction of future Y values. So how does that work in practice? In practice, we usually use linear autoregressive models, and we model yt as a function of past values of yt minus 1, yt minus 2, etc. And then we make another regression where we include also past values of variable x. And if the residual variance decreases, we conclude that X causes Granger causes Y. And that's what we call pairwise Granger causality because we only have two entities there. You can then create a measure of effect size by using the logarithm of the ratio of the variances. And this is something that's been done a lot, both in econometrics, where you have figures such as Granger, Sims, and Geweke who use this a lot, and also in neuroscience. In neuroscience, there's quite often spectral versions of these techniques, but it has also been used in genetics and a little bit in ecology as well. So what you may be more familiar with is this paper by Sugihara and co-authors in 2012, detecting causality in complex ecosystems, where they suggested two things. First, that Granger causality will have issues with nonlinear, highly nonlinear processes, and that it would work only for linear stochastic systems. So I will make a little more precise later on what we mean by linear stochastic systems. And they developed a new method, convergent cross-mapping, to improve or inference of such dynamical systems where the state variables are a little bit entangled, in the sense that it's difficult to differentiate the information that's only in the predator or only in the prey, for instance. So they talked a little bit about separability issues, that you cannot separate this information contained within X or contained within Y, but I prefer to talk perhaps about entanglement between the state variables, because separability has many different meanings in mathematics, and it wasn't made precise exactly what it means here. So I will take the figures from Sugihara and Kohoto's paper to illustrate a little bit how convergent cross-mapping works. So on the top left panel, you have the Lorentz attractor, which is the endpoint of the trajectories of the Lorentz dynamical system, which is famous for exhibiting the butterfly effect. And it has three state variables. And due to Taken's theorem, we know that we can actually reconstruct this attractor using a single state variable, but three delayed coordinates. So here you can create a reconstructed attractor mx using xt, xt minus tau, xt minus 2 tau. And you can do the same for my, so you can have replicate versions of your attractors using x or y or z, for that matter. And Sugihara and Kohoto showed that if in the dynamical system x is causes y, in the dynamic interaction sense that I showed you earlier, you can actually predict xt values from this reconstructed attractor my. So the way this goes in practice is that you reconstruct several versions of the attractor, and then you compute a correlation coefficient between the true x values and these x values reconstructed from my. For instance, in the predator-prey example that I showed you earlier with Didinium, the predator, and Paramecium, the prey, Sugihara and Kohotos, they showed that, for instance, if you look at Paramecium cross-mapping Didinium, which means the Paramecium time series predicted by the reconstructed Didinium attractor, it has a high correlation between predicted values and true values. And this also increases with the library size used to reconstruct the attractor, which is a signature of causality. So here in this example, you have a causality from the predator towards the prey, and the prey towards the predator. So I haven't commented on this yet, but the way you do the cross-mapping is a little bit counterintuitive. And some people have called this causality reversion, which means that when the prey cross-maps the predator, it means that the predator causes fluctuations in the prey, which looks a little bit opposite to what happens with Granger causality. So with Granger causality, if X causes Y, then we say that this is equivalent to having X values that are better predicted when you use information about both X and Y rather than just about past values of Y. So both methods look like they're very different, although, as we will see, this is not exactly the same thing as predicting from the attractor as predicting future values. So the methods might be more similar than they appear. So Sugihara and co-authors suggested that Granger causality would apply well only for linear stochastic system, and that forces us to make more precise what's a linear stochastic system. So in ecology, what we use that would fit best these definitions are multivariate autoregressive model of order 1. And in fact, these are linear on the logarithmic abundance scale. So what you usually do is you take a time series of abundances and you log them, and then you relate xt plus 1 values to xt values through a matrix B, which encapsulates the interaction coefficients. And then you can add some other random fluctuations like those induced by the covariates UT and random noise ET here. So in this matrix, a non-zero entry means conditional Granger causality. So B21, for instance, is the effect of species 1 on species 2, conditional to all other variables, all other species, and also all other abiotic variables. So it's a slightly different concept than pairwise Granger causality that I showed you earlier. An important question is why logarithms? Why do we use this log transformation? And it's for two reasons. So the first and easy answer is that population size are logarithmically log normally distributed. That's something that we observe very often. And another reason is that most of the processes we're looking at in population dynamics and community dynamics are multiplicative. So the log transformation is a natural transformation to get from a multiplicative scale to an additive scale. And if we back transform this model, we see that it's actually a power law model. That's what I'm showing here in the equation. And as we know, power laws are fairly good to represent monotonic nonlinearities. So this suggests that these models, just by adding a little bit of a log transformation, might be more robust to nonlinearities than one thinks. And that's actually what we found doing a survey of the robustness of a multivariate autoregressive model of order 1 with my colleague Grégoire Certain and also with Anna Goldmark. We found that most of the signs of the interaction matrices were recovered correctly for a number of two species and a food web model. So these were modeled mostly with fixed point equilibria, which means they're less nonlinear than limit cycles or chaos, for instance. So this had some limits in terms of generality. But in general, when we use Granger causality, we use more time lags than just one, as in multivariate autoregressive model of order 1. We can use, you know, 2 time lags, 3 time lags, perhaps in some applications with a lot of data, as much as 10 time lags. Usually we try to keep it small to 2, 3, 4 max. And an important fact is that with a small increase in the number of time lags, you can have a large increase in the flexibility of the behavior of the dynamical system. So a simple linear autoregressive of order 1 cannot show population cycles because it has a fully decaying autocorrelation function. But autoregressive model of order 2 can already have cycles of any periodicity possible. And also you can tune the amplitude of a simple single species autoregressive model to match a little bit what you want. So of course this won't be perfect. It won't perhaps capture all aspects of the dynamics, but it will give a good first approximation. So the bottom line is there are many reasons why Granger causality might still work for highly nonlinear dynamical systems. So what we decided to do is to re-evaluate the relative performances of Granger causality and convergent cross-mapping using a number of time series that range from highly nonlinear to close to chaos, and to quite linear in the sense of multivariate autoregressive model of order 1. And of course, what we expected when we started this was to find that convergent cross-mapping was really good on the cases close to deterministic chaos, strong chaos, and then that Granger causality would get better and better as we go towards more linear dynamics, which makes sense. But in fact, this is not what we found. So let's see what sort of data and models we've used. We've used the paramecium didinium data that I showed you earlier, for which we find reciprocal causation using the convergent cross-mapping already. Then we've used the chaotic two-species competition model. All my competition models are asymmetric. There is a strong interaction and a weak interaction, so that we can see which one we can get. And then we crafted new competition models. So on top, you have a Ricker competition model, which is a little bit similar to the previous competition model, but with a slight difference in the shape of the density dependence. And to make things a little more difficult for our statistical techniques, we decided to incorporate a shared abiotic driver in green, where you have a perturbation like temperature, which is affecting both species in the same way. So you can think of it as a confounding variable. And of course, we consider all of these models with interspecific interaction and without interspecific interactions to be able to evaluate for false positives. Now we've decided to step this up, and we've also done 10 by 10 interaction models, where we have here a Lotka-Volstaage system where the interaction matrix is for 10 species, and to be able to evaluate both false negatives and false positives at the same time, the matrix is modular. So you have 3 modules here. The third module is independent from the rest, and the 2 modules are connected by 1 species. So it would be interesting to see if we can get in our final outputs both the modules that are in this interaction and also the connector species between them. And this model, for the parameters that we've chosen, it has a positive stochastic Lyapunov exponent. So it's in the range of stochastic chaos. Then because we wanted to have large dynamical systems that are not all nonlinear, we considered just a linear approximation of this model, which we did by computing the Jacobian. So we use the Jacobian and we add noise to it, and this is the linear approximation to this model. And then finally, we did 20 by 20 interaction models. So not all species interact with each other. You see here the structure. So when there's a link, there's a 1. When there's no link, there's a 0. And we try to have a structure that preserves this modular aspect, and also some of the modules are connected with each other. And in that case, to obtain different results at each simulation run, because this model had a stochastic Lyapunov exponent close to 0, we change a little bit the coefficients that are allowed, the interaction coefficients that are allowed to vary between a maximum and a minimum value. So each simulation is a little bit different, although the structure does not change. Now we have to evaluate if there are interaction between those models once we have the time series. So for the 2 species models, we've done it with 300 time steps. And we did pairwise Granger causality tests using alpha of 10% and also an effect size threshold. So those who know well statistics are probably wondering why an effect size threshold. So if there are no interaction between the species, you should have uniformly distributed p-values. But this happens only if the model with which you simulate is exactly the model that you fit. And this is not always true. So having an effect size threshold allows to weed out those statistically significant effects with very, very small effect sizes. That's the main reason why. Then we selected a number of the time lags with BIC, which is classical. We did val tests using the Granger test package, no, the Granger test function within the LM test package. And then we also use for conditional Granger causality, the causality function in the vars package, if you're interested in doing this. For convergent cross-mapping, we also had to use an effect size threshold of 10% on this rho coefficient, which is the effect size, and we use the same thing, the same level of 10% for the tests. And then our p-values are surrogate-based. So time series surrogates are a way to produce a null hypothesis by removing the cross-correlation between your time series. In the simplest case, it can be done by just permutating the values of your abundances along the time series. In more complex scenarios, like when you have a confounding abiotic driver, you have to also conserve the spectral color of your time series. So it must have the same Fourier spectrum, which we did. We also compare these p-values, these surrogate-based p-values, to p-values based on the convergence with respect to library size, which had been crafted by Kobe and Baskerville. So that was for the two species model. We did this more or less the same thing for the many species models, but we had to increase the number of time steps for 20 species. And also we had to add the Benjamini-Horschberg correction when testing to control for the false discovery rate. And finally, instead of doing pairwise analysis, so a large number of tests for when you have 10 by 10, for instance, you do 90 tests. We tried to fit the whole dynamical system in the Granger causality case by fitting multivariate autoregressive of order 1, which have some LASSO penalties. So actually, the penalties are not exactly the LASSO, for those who know the LASSO, because we know that there's a modular structure in there, and we have to take into account this modular structure if it is present. And for this, you need something like the adaptive LASSO, and we use a weighted LASSO approach, which is a sort of a mix between the group LASSO and the adaptive LASSO. So this is highly technical, and for the details, I referred you to this very nice paper by Camille Charbonnier, but I just pop up the equation so that you know what's in there. But for those who know the LASSO, you have the classical least squares there, and the penalty that is used is structured by classes. So we have an indicator function that says if two species can be connected or cannot be connected. And then there's a mixture model, which is fitted at the same time. So I won't go into all the technical details. We have in the paper associated to this, we have an appendix in which we give a little bit of detail. And then in the original papers, you will find the whole thing. Basically, after we selected the structure of the network with the LASSO, optimizing the tuning of the penalties is done with BIC, which is a classical choice to find back the right model when you want consistent estimation, when you want that if you have an infinite sample size, you always find the right model. That's what BIC does. So enough with the methods. Let's go to the results. So I present to you both sensitivity and specificity. So sensitivity is the true positive rate. How many of those interactions do we find? And I will start by describing to you the results for deterministic chaos. So for deterministic chaos, in blue, you have the result for Granger causality, and in black and gray, the result for convergent cross-mapping. And so when it's dark, it's the strong interaction, and when it's light, it's the weak interaction. So as you can see, you find almost all of the strong interaction and about 50% of the weak interaction, both for Granger causality and for convergent cross-mapping. And the average performance is the same, which was really surprising because we thought like in that case, convergent cross-mapping will work perfectly, and then Granger causality like multivariate autoregressive model fitting won't work at all, but it does fairly well. And the false positive rate, so specificity is 1 minus the false positive rate, is quite reasonable both for Granger causality and convergent cross-mapping, even though in that case it's a little bit higher for convergent cross-mapping. Then for the two species here is the recur competition model that I showed you earlier. And in that case, everything works fine, both for Granger causality and convergent cross-mapping. And then if we add an abiotic driver like temperature, which is confounding the dynamics and pushing it in the same direction for both species, things are a little more difficult. So what you see in the graph is that the strong interaction is well recovered, but the weak interaction is completely missed by Granger causality, although it's correctly captured by convergent cross-mapping. But the story is a little bit more complex than that, because convergent cross-mapping also has more false positives. So one method is very good at finding interaction, and the other is good at avoiding false positives. If we move to many species, we have, so Recur 20 is this discrete time Lotka-Volterra version for 20 species, and Recur 10 for 10 species. And MAR10 and MAR20, these are the linear approximations of those models. And as we see, the average performance of Granger causality is fine, while convergent cross-mapping, in that case, did not find back correctly the interaction for 20 species. This can be due to the number of things. And then the false positives were quite okay overall, although a little bit higher than they should have for convergent cross-mapping with 20 species. So overall, both methods work, have similar performances, which really wasn't expected. We expected that when we had highly nonlinear dynamics, convergent cross-mapping would dominate. And then when we had quite linear dynamics, Granger causality will dominate. So we should have had patterns where the scores decrease from left to right in those panels, and that's not what we observed. So I show you here the same results, but a little bit differently. So the results you've just seen for many species, they are on the top left panel because these were results for pairwise testing. So what I haven't showed you until now are the results for these LASSO style multivariate autoregressive models. And these are on the top right panel using the method Simon, which is for modular interactions. And as you can see, you have the sensitivity on the y-axis, and you have the false positive rate on the x-axis. So we want a low false positive rate and a high sensitivity. And as you can see, for the multivariate autoregressive model, when we simulate multivariate autoregressive model, this Simon algorithm is doing really well. But it's not doing so great when we simulate a highly nonlinear Lotka-Volterra. So what that says is that this LASSO-style parametric method is a little more sensitive to parametric assumptions about the community dynamics. The result I just showed you for convergent cross-mapping are in the the bottom right panel. And we also tried different types of p-values, p-values that are defined by convergence with respect to library size. They have been crafted by Kobe and Baskerville, and these are on the bottom left panel, and they did not really improve the performance. So now I will show you a little bit what the networks look like. And you should see a lot of green in that figure. We had a referee, we had lots of blue before, and when it was doing good, and a lot of red when it was doing bad, but the referee suggested that it wasn't a good color code. So I changed everything to green. So large green circle were, or when things are doing, when the technique is doing well, and large squares, or when the technique is getting us false positives. So as you can see here, on the top left panel, for instance, you get fairly well the modules that we had previously in our interaction matrix. We had 3 modules, and with 1 connector species here, and we see those 3 modules, and we see the connector species, and there's only one place, the big square, when there's really a lot of false positives. And otherwise, when there's no interaction, we have a tiny amount of false positives on both sides of the diagonal. If we simulate data not with Lotka-Volterra, but with the multivariate autoregressive model, we have observed roughly the same thing. Here, there's the diamond is that there's one interaction which is missing, but it's only one amongst many. And if we go to the bottom, we see that convergent cross-mapping has similar performance, even a little bit better in that case. It's doing really well. Then, if we look at the other types of algorithms that we've considered, this LASSO-based MAR estimation is doing a little less well for Lotka-Volterra, while it's doing really well when we simulate with a multivariate autoregressive model, which confirms that it's a little bit sensitive to parametric assumptions. And then these other types of p-values with convergence to library size for convergent cross-mapping are not doing so great. So if we go to 20 species, which you know, starts to be quite a challenge, with Granger Causality, for both Lotka-Volterra and MAR simulated networks, we have this nice recollection of the modules and also the connecting species between them. So we get very well the structure of the network, and there's a very low amount of false positives. And in that particular case, convergent cross-mapping is not doing so great and is having quite a bit of false positives, and also not finding all the interaction in all cases. And so when we use the LASSO-based multivariate autoregressive model to estimate the interactions, it goes really well as well in this 20 species case. And for some reason, the convergent cross-mapping didn't work great in that case, but that may be just because there's more tuning which is necessary for those p-values in that case. So just to conclude on 2 species systems, In most of or two species cases of fluctuating community dynamics, we find that both linear Granger causality and convergent cross-mapping are working fine. This was a little bit surprising because this paper by Sugihara really suggested that Granger causality wouldn't be working at all. So I was skeptical that it wouldn't be working at all, but I did not suspect that it would work equally well. That was really surprising. And probably the differences that we had with Sugihara and co-authors is because we use BIC for model selection, while they use a sequence of likelihood ratio tests. And I think this created some over-parameterized model on their side, while we had relatively low dimensional model on our end. There's one exception, which is when you have two species, they're competing strongly, and there's a confounding abiotic driver, which is making their dynamics both go in the same directions. That's difficult, and in that case, Granger causality produce some false negatives and convergent cross-mapping some false positives. This is known to be difficult even when you have a single species and you try to estimate density dependence. And we've shown in additional simulation that actually this is due to the fact that you have both a strongly autocorrelated environment and strongly nonlinear dynamics. If you have either an uncorrelated environment and strongly nonlinear dynamics, or mildly linear dynamics and an autocorrelated environment, this works. It's when you combine strong linearity with strong autocorrelation in your abiotic variables, then things crash. So the bottom line overall is that there's nothing wrong with using Granger causality techniques for limit cycles or chaotic attractors. In many cases, it works. And there's also nothing wrong with using convergent cross-mapping for stochastic system, even though this method has been developed for deterministic dynamical systems. And the reason why probably these methods say a little bit the same thing, if we go back to the definition, is that what is an interaction is defined in the same way. In both methods, we think that there's an interaction between species J and species I if the population growth rate of I changes as population density of species J changes. Now moving on to many species systems. And I agree that it may sound a little bit ridiculous when I say that many, is 10 or 20 species. I guess, some ecologists would probably prefer that I would say 100 or 1,000. But unfortunately, I must admit that we're probably not quite there yet in terms of fitting models for 100 or 1,000 species. So we find, quite surprisingly, that just having a false discovery rate correction and testing pairwise was quite efficient. It's a little bit surprising why the LASSO technique that we used wasn't better. As I said, there's probably a little bit of sensitivity to parametric assumptions. But also one possible source of issue is that we use a maximum time lag of p equals 1. We didn't use higher order time lags, higher order delays when modeling, like using 2 time lags or 3 time lags. In that case, first because the nice package for modular networks that we used only functions with p equals 1, and also because when we selected the number of time lags with BIC, it suggested p equals 1. But it may well be that if we allow the number of time lags to increase, the performance of these LASSO techniques will increase as well. So there are techniques that allow to do that. That are a little bit tricky, but there's a package using group LASSO developed by Nicholson. The package is called BigVar. And there's a lot of improvements at the moment in this high-dimensional multivariate autoregressive modeling. And there's been recent reviews in Bassu and Matson and Shoja and Fox, which are really must-reads if you're interested in these sort of things. So far, of course, avoided mixing strongly autocorrelated environmental forcing and many species with nonlinear dynamics, because we don't know how to do that yet. But obviously, that's one nice thing to tackle in the future, because there's no reason why in real life this would not happen. So just to give a little bit of perspective after this this conclusion on what you can do with these methods, we've functioned under the assumption that there's a sparsity in the interaction matrix, that either there's an interaction or there's not. One possible alternative is to abandon the sparsity assumption and think that it's all shades of gray. There's always an interaction between the species. It's just they're more or less strong. And this is a little bit what Ovaskainen and co-authors have done, using a different approach to avoid fitting a full matrix without constraint. They used what is called in statistical low rank approximation, where they fit the model to many species. Actually, they have 100 species. And they do something that looks like a PCA here, where their interaction matrix is structured with a low number of dimensions. And I really recommend reading the paper if you're interested. And they have some simulations as well, which suggest that this approach, which they call the community level drivers approach, is doing overall better than the sparsity approach. Which, of course, it might, if you do slightly different simulations or you use slightly different data, the sparsity approach may prove better eventually. There's probably something to left to the appreciation of the analyst there. And there's multiple other low-rank estimation methods in statistics that are currently being developed. So probably many other things like that will appear in the next years. So the paper is now published in Theoretical Ecology. I realize I gave a lot of technical details in this talk, but there's more in the paper. And we point out to other kinds of methods as well that might possibly be used. My overall take on this is that the question to choose between Granger causality, multivariate autoregressive models on the one hand, and convergent cross-mapping on the other, is not a question of what type of dynamical system is there, but what you want to do with it. If you want to just look at the shape of the attractor, obviously methods that reconstruct the attractor are best. If you want a parametric method in which you control well the number of false positives, then Granger causality might be more useful. So there's all the code as well on GitHub, and feel free to email me if you're trying to use this, or if you have technical questions. I think as follow-up questions on directions in which we should develop the modeling. One key issue is how to better interface this sparse or low-rank interaction matrix representation with things that make ecological sense, like modularity and other kinds of network properties that we know to be there in ecological networks. And another related question is how to incorporate prior information about those interactions, because obviously if we want to fit these type of models to high dimensional systems, we most of the time have to implement constraint on the interaction matrix so that we can estimate this with a little bit shorter time series than what we used here in this theoretical exercise. So on that note, I thank you very much, and I will await the questions.